Yeah, a little weird week in that we had the exam over the weekend, so I totally forgot about a new video until it was Tuesday, so I put it out on Tuesday. So things are a little bit late. Okay. I put a video out about the exam, so in case you haven't seen that yet. Yeah, a few irregularities. Some people just cut and paste answers from the web, which was interesting. I didn't think to say your own words because I assumed that was assumed. Apparently that was not assumed. So yeah, general rule, don't copy and paste on exams ever. But anyway, yeah, and then there were a few odd things that there were repeat things, like people kept saying on the quick sort that it was a sort based on value, not position. All sorts are based on value, which I didn't understand. That clearly they had read that somewhere, and it wasn't wrong or right. I mean, if there's more to the answer, it was fine. But I just thought that was weird. That was a common. I mean, more than 3 or 4 people had that in their answer, which is strange. And the other strange one was that several folks said that divide and conquer are always n log n and brute force are always n squared, which that's not correct either. It depends on the algorithm. So a few oddities, they're all in the video, so we won't spend any more time on that. But I do encourage everyone to take a look and see what I've marked off. And if I misread what you wrote or you think I got it wrong, I very well could have. Let me know and I will be happy to take a look and regrade whatever's necessary. Okay. I think the class average was an 85, which seemed reasonable. So not bad at all. Okay, so let's talk about this next chapter, see what questions you have. So this chapter is on space and time trade-offs, which just means that we can do something that takes more storage in the hopes that it will lead to a quicker algorithm later, quicker performance. So they also call it input enhancement. Okay. So the sections here, the first section on counting methods for sorting, I mean, that was interesting enough, but there really weren't any good homework problems from that. So I think we can mostly ignore that unless you have specific questions. The next section was on the string matching. And I like the idea of the horse spool algorithm there. The Boyer-Moore is probably more detailed than we want to get into, but we can certainly talk about that if you want to. So that's an example of what the book calls pre-structuring, where you're going to make up your symbol table, make up some things in advance so the searches go easier, okay? And then section 7.3 is on hashing. Hashing's a data structure that you should know something about. Hopefully you hit data structures. Maybe you did, maybe you didn't, but we talk about hashing. And then in section 7.4, we talk about indexing with B trees. B trees are highly important of a data structure. They're basically indexing. So they're not binary trees in the traditional sense that there's a node with 2 children. These will have multiple, more than that children. But it's kind of the idea, as I think I said in the video for the material this week, that when you have an encyclopedia, you don't have one giant volume. You know, it's 3 wide, 3 feet across. Instead, you have indexes. You know, you have the A's, the B's, the C's, and it can break down even further in some cases. Okay, so that's the idea of a B tree, that that you have a tree that has built-in indexing to get you closer and closer. All the data stored in the leaf nodes, but it gets you closer without having to follow the whole thing. It's kind of like a binary tree, except that it allows for a lot more data to be processed. Okay. Databases work using B trees. Memory in our operating systems often work using B trees. So it's pretty important data structure. Okay.
I had a question about the B tree because it has to do with the homework problem.
Yes.
So when you're inserting something and you have to end up moving, you know, something up or whatever.
Yes.
And so it said a lot, like when deciding what to move up, you kind of like take the average, I think is what it said. I'm trying to remember. But I mean, if you take the average, it's going to be a number that's not in the tree.
Right.
So we don't want to do that, right? I mean, we just take.
I don't think it matters. The leaf nodes have to be something that's in the tree.
Right.
But I don't think there's a requirement. I mean, in the example, they all are.
Okay.
But I don't know that it has to be that way. But if you wanted to keep it, you would just take the average and then get the closest element to that.
Oh,
Would-
okay.
Okay, if that makes sense. Yeah, I'm not sure if they say that or not. I'm sure they do.
Yeah,
say
I couldn't, I was trying to look back, like I had watched the video and everything, and I don't remember that being in there. And so, or it said something about like it being the average. And I'm like, well, if we take the average of these, it could be a number that's not listed.
Right. Yeah, but I think you can force that to be one of the numbers that are listed. And I think that may be
Okay.
the safest way to go. Okay. But again, hopefully you can see it on the screen here. I try to make it bigger tonight. I think the big thing about the B trees is that they do have multiple, this is order 4 because there are 4 children, but there's only 3 data points per node. And you draw it this way because each of these is like where the pointers come out of. So this one's going to be less than 20. Okay. This one's going to be, this guy here is greater than or equal to 20 and less than 51. Okay. And then this one is going to be greater than or equal to 51. Okay. So that kind of is how those get read and put together. Okay. But none of these are really data. These are all indexing. Okay. The only data is down here on this bottom row. Okay. The bottom row is where all the data is stored. Okay. So these are used just to get you there quicker. Okay. So for example,
when we're inserting things, is it a good idea to like put it into the leaf and then modify it up as we go?
well, sometimes you're not sure which leaf you're going to put it in. So if you,
Well, it can't be, if it already has 3, then it has to be in one that doesn't have 3.
well, it depends on where it's at. Like if we wanted to add 47, okay, we've got trouble, right? Because 47 has to go out of this link because it's less than 51. Okay. This is already full. Okay. This is already full. Okay. So we would have to split this one up and basically move the 40 to this box. So we could put the 47 in this box and then have to switch that probably to the next element that's there. Maybe the 43 would work there.
Okay.
Okay. So yeah, it's kind of, you just kind of move it around to make it work. But that's the general idea, that you split them up when you have to. Okay.
So for the homework problem, you don't care about actually seeing us move things. You just want to see the finished.
Yeah, that's fine.
Okay.
Yeah. If not, that's a lot of drawing. Yeah. Not sure if they give an algorithm for that or not. They do not.
No, there's no algorithms in there for that one.
Nope. So I guess you just have to make it up and make it work.
So on that one, since you're for the question
Uh-huh.
or the homework question,
Right.
since you're inserting 2 elements that would end up being in the same leaf,
Right.
You have to promote up to the center level and the top level then, don't you?
Yes.
Okay.
Yep. And you've got capacity. I think you're inserting in this 7-9, right? Isn't that what you're doing? They don't give you another graph.
Yeah, in
I
7,
thought
8.
it was 7-8 actually.
Oh,
Yeah,
gotcha.
it's
So it's
7-8.
before that one. Okay. It's that one before the 65 gets added. Yeah. Yeah, you start from here. Okay. And you've got plenty of capacity. It just depends on where they want to go, what you have to do with it. Okay.
So my other main question was back in 7.3 with the hash tables.
Okay.
Like I was fine making them, but I don't think I understand the idea of the key, like what it means by key comparisons and asking you to find the largest number and the average number.
Right. So what the idea there, let's say we're doing the closed hashing, which means it all stays in the array. There's no linked list. Okay. Which is also open addressing, which just makes no sense that the closed and open are the same. Okay. The number of key comparisons, let me go to the unfortunate drawing with my mouse. I think I need a new mouse, not even a very good mouse. Okay. So the idea being, I'm not going to do that. Instead, I'm going to go to Excel because Excel, at least my boxes will look up boxes. Except Excel seems to have gone away. There's Excel. course, Excel is going to take all day to load. Share the screen here. Okay, so let me make this a little bit bigger. Okay, so let's say this is our hash table. So as far as key comparisons go, if it goes to 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, okay, we're going to be doing a mod of 11 to get there is one way to go, right? So that's what it's going to go to, okay? Why that just disappeared, that's very strange. So when looking at the number of key combinations, if we have something stored here, okay, so 16, no, yeah, 16 would go there, okay? Let's say, no, yes, let's say 17's there, let's say 18's there, okay? You could be things, but you get the idea, okay? Then the maximum number of key comparisons. If I want, why does it disappear? That is so weird. If I want to store something else that would go to 7, say just 7, okay, would mod out to 7, okay? I would try to store it here. I can't. With linear probing, I would instead store it there, okay? So if I were searching for 7, I would start by looking here, but I have to look there as well, okay? So the worst case scenario, if I'm looking for something, so if I wanted to add something else like a 5 would go way over here, okay? And given what we have, that makes it the worst case key comparisons. I would have to, again, I'm searching for a 5. That's going to give me my h of hash function on that k. It's also going to equal 5. Okay, so I look in the 5 spot. There's something there, but it's not 5. That's one key comparison. Okay, I have to do another one there. 2, 3, 4, 5. So in this case, there's 5. Okay, so given the current fullness of your hash table, the longest string of consecutively filled cells gives you the worst key comparison. Okay, because if there were a space there, then I would only have to check 2. Okay, but since there wasn't a space there, I have to check all those. Okay, so that's kind of how that works. And then if you had the open addressing, okay, with the linked list, then whichever of the linked list is the longest. If you have one linked list that has 10, well, then if you had something you're searching for whose index was that position that had the 10, but it's not in your hash table, you'd have to search all 10 of those. So in that case, the maximum number of key comparisons is the maximum length of any of the linked lists. Okay, that makes sense?
Makes sense. Thank you.
You're welcome.
All right, so how do you get the average? Which is part C of those questions.
Is that the part C's are always a killer, aren't they? Let me take a look at the question here. Let me find.
Yeah, it's just construct the tables and then find the largest number and the average number. That's all it's asking for each one of those.
But you have actual data, right? That you're putting in the table?
Yes.
Okay, so the average then on all the things that you can look for. So it's if it's the linked list one, then it would be the average length of your linked lists, right? And if it's not, it would be you would take an average of all those strings of characters that have spaces between them. If there's one that's 5 and one that's 4 and then one that's 8, you would average those together. Okay, does that make sense?
Do you include ones that have 0?
Nothing would have 0. Everything would have at least 1.
Because this table, we have only 6 data points or whatever to put into it, but it has 11 spaces or 10, 11 spaces.
Right,
so,
but those would still be 1. If you were searching for something that's there, you wouldn't find it. But you would still search for that one key. You do one key comparison and see that there's nothing there.
Gotcha.
Okay. But they're saying for a successful search. So they're saying, so that's a little bit different question. So let's do this differently here. So this is the closed hash table. So this is going to be inside of this is going to use a linear probing. It's not the it's not the linked list ones. Okay. So in this case, we only have successful searches, 6 things we can be looking for, right? Each of those has a number of key comparisons it will take to find them. Add those up, divide by 6, there's your average. Okay. Well, I thought they did mod 11, and my random example is also mod 11.
I thought you did that on purpose.
Nope. That would make way too much sense. So if that's still unclear, I mean, that's probably the most difficult thing. I don't think we have a lot of questions. We probably have the time. Let's go ahead and take a look at this one in a little more detail. Okay, so if I copy the data over, since I've already got the table drawn, but that's way too small. Okay, so I've got 30, I've got 20, I've got 56, I've got 75, I've got 31, and I've got 19. Okay, so my indexes then, I should be able to do, I wonder if I can do, I probably can't do that. I probably have to, nope. There's probably a modulo function. Well, okay, I want a mod, hopefully that's the modulo.
We're not seeing what you're working on.
Well, of course not. That'd be too easy. Thanks for letting me know that. I hate, sometimes students just sit there and you're like, I could have showed you if you just would have let me. I know, I'm trying to do what you want. Okay, so that is what? J10. 11. Okay. Okay, so this should be the values that we need, right? So I can then use that. So the 30 should go in position 8. The 20 goes in position 9. 56 goes in position 1. The 75 would go in position 9, but it can't, so it's got to go to here. And that's going to be contrary. Okay. The 31 also goes to 9. Okay. So it can't go there, can't go there, but they are circular. It goes back to the 31 being over here. Okay. And then the 19 is at an 8, okay, which is more of a mess. It can't go in the 8, can't go here, can't go here, can't go. I wanted to go back, wrap around my back, like can't go here, can't go here. It's got to go all the way to here. This is a poorly designed table. Okay. So now you have to look at the number of key comparisons for a successful search for each of these. Okay. So when I look for the 30, it says to go to an 8. I find it, just one. Okay. It's bigger before I hate life. Okay. So when I search for the 9, the 20, okay, it says go to 9. That's there. We're good. There's one there too. Okay. The 56, it says it's at 1. I go to 1. It's good. We found it in 1. Okay. I say for the 75, it says that it's a 9. Okay. Key comparison there. No, 1, 2, it's there. So we got a 2 there. Okay. A 31 also says it's a 9. Okay. So that's 1 comparison, 2 comparisons, 3 comparisons. Okay. So there's the 3. And the 19 says it's at an 8. Or says, yeah, it's at position 8. I put that the wrong thing. That should be a 19 there, not an 8. So I look here, it's not there. It's 1 comparison, 2, 3, 4, 5, 6 comparisons to get the 19. Okay, then I can equal average of all these. So the average is 2.33. Make sense?
Yep, I had done it right. I just wanted to confirm that I had done it
Yep.
right.
Yep, that's good. I didn't know it gave you data. I thought it was trying to do some kind of theoretical thing, which gets a little more difficult, but yeah. Okay. Other questions? There wasn't a lot here, and it was kind of on purpose. You know, we just had the exam. I didn't want to kill everybody.
And next week's Easter.
What's that?
And next week is Easter, so please don't kill us then.
What's the next chapter, I wonder? We're not doing the next chapter, are we? We're not doing
Chapter 9. I don't
yeah, we're
remember
not
what it
doing
is.
dynamic programming. We can go ahead and give a little review here. Chapter 8's interesting if you're weird like me, but
Greedy. That's the next one.
Greedy's fun. I think I like greedy. So just in time for Easter, we're going to get greedy. Seems like it's not really in it's not really the way the week should go, but that's how we're going to do it. But yeah, I think that'll be relatively straightforward as well. That won't be too bad. Okay. Again, this chapter peaks in difficulty in chapter 2 and then gets a little bit better. Any other questions?
Can we talk about, I got these right, but or in 7.2 doing the horse bulls, I did the problems and I've gotten them done, but I wasn't completely sure about how to make the shift table. Like, I understand that, like, if a letter is not in your like code or text or whatever,
Right.
the number is the length of your little thing you're searching for.
Right, because you can go the
So
whole
if it's
way.
a 6, right?
Yes.
So I guess I wasn't as sure about with the letters that were in it, how they got some of those numbers. Is it from where the letter is to the next one of that type, or just to the end if there weren't any more?
To the next one of that type, because it's how far you can go.
Okay.
So
Like Barber, the A, it was 4
right,
because there were 4 letters after Barber and there are no more A's.
right.
But B, that first B, there were 2 spaces and there's another B. So
Yes.
that's the process behind that.
Yes, because
I had to
what you're
kind of
trying to
work
do,
backwards.
you're trying to see how far you can move over your pattern to have to look again. Okay.
Right.
So if the letter's not in the if the letter you find is not in the pattern, you can do the whole thing because that slot cannot be part of your pattern. So you can go all the way past it. Okay. But then depending on what else it is, the letter that you find, if you find an R and there's an R in Barber, well, then you move over to that R. And that's what you're doing physically, but you can count that up and not have to, computers have a hard time seeing and knowing where to move it. So you're doing it in an algorithmic fashion is how that works.
Because I was just working backwards trying to figure out those numbers, but I did figure it out and I got it all, both those problems to work.
Mm-hmm.
So I just want to make sure that was the right way to think about it.
Yep. You're thinking about how far can I move this pattern over to start searching again, guaranteeing I'm not going to miss anything.
And it's lining up the last letter with whatever.
Yes.
So if it's the same, then we do that, or it's the last letter lining up with this letter. So if this letter is in my phrase or whatever, then I need to look at that table and move it over that many. If it's not, then I move it over the length of the text.
Yes.
Okay.
Yep. And that makes a big difference in searching compared to the sequential. If there's a lot of data, that really makes a big difference in how it works out. Anything else you want to talk about?
I'm good. I liked this chapter.
I did too.
it's a good chapter. I think you'll like Greedy too. I think Greedy's a good chapter. It makes sense. We're trying to find, we're getting into, there are problems that are, we've already mentioned them before, that there's no good way to solve them. Things like the traveling salesman, things like the knapsack problem. So even though there's no known solution in polynomial time, okay, there's nothing but brute force. Really, well, no, that's not true. There's nothing really good, but there are some techniques we can use, and the greedy technique is one of them that we can use, okay, to help us get there, okay. So I think it'll be kind of fun. Okay, well, if nobody else has anything else, we'll go ahead and call it a night. And if you do have questions later, just let me know, and we'll work them out. But this was meant to be a fairly light homework week, so hopefully that turns out to be the case. So, okay. Well, I will see you guys next week. Then it should be another video on Sunday. We'll be back to our normal schedule this time. So,
Thank you.
Thank you.
see you later.